Hello, my name is Parsa Kazrani, and I'm working with Catherine Lee, Kenzo Prayer, and Jake Zhang to basically do a unit review on the Unit 7 content. And right here is all the Unit 7 content that I'll try to be covering within the following 7 to 12 minutes. It's basically all of this, so primarily equilibriums. Pick this because honestly, equilibriums are going to be one of the most important chemistry topics that you're going to have to know for future courses as well. And I'm going to try to focus more on the conceptual things. I'll talk a little bit about math, but I also want to primarily focus on equilibriums in and of itself. So I won't really cover that much about free energy of dissolution, simply because it's a little bit, or it's very loosely connected to equilibriums, and I'd rather just primarily not deviate from the main concept. Anyways, with that being said, it's really important to begin asking yourself, what is an equilibrium? So, what is it? And the best explanation is that the rates of reaction are equal. So the rate of reaction, which I'm going to denote in the rest of this video as the ROR, is equal for both the forward and reverse reaction. So if that's the case, right, and if I were to essentially draw a fake chemical reaction, A plus B becomes C, assume that I have a thing like this. So this is, let's say, a second order overall reaction with respect to A and respect to B. And this is the forward reaction, right? These are just the rates of reaction, right here, the way I've denoted it. So I'll just call it R forward. And then there's also a reverse reaction. So previous content had covered that when there is a forward reaction, the backward reaction is also occurring as well. But in an equilibrium, the most important part is that the reactions are occurring at the same rate. So if I were to then write out the rate of reaction, but in this case, I'm going to write little r for reverse, is equal to Kr, right, of just C. If I were to put these two to become equal, right, so Rf is equal to RR, which is essentially what I've been saying as, what a equilibrium is. You're going to basically have this type of formatting. Okay. And to make it simpler for myself, what I want to do is I want to keep all the K's on one side and the concentration notations on the other side. So I'm just going to do some basic algebra to basically get the following, I guess, notation for equilibriums. And this is typically how you're going to always see equilibriums represented as, or at least their constants. And it's really in this format where you're going to have the product concentration on the top, product concentration at the top, and then the reactants at the bottom. Okay? And this right here, this Kf divided by Kr, if you were to just simplify it into one value, it's just going to be denoted as K. K doesn't have any units, so K is no units. And K is literally just the value of all of the concentrations of reactant and product divided by, the product divided by the reactant. And it's simply just a value of that. That's literally it. It doesn't have any units. It's not like joules or anything. It's straight up just that. The reason really for that is because if you have, and this is just mathematically speaking, if you have molar here on top and you have molar on bottom, they just kind of cancel out. And also it's just for scientific notation. Scientists haven't chosen units. But so now that I've identified that K is what we call the equilibrium constant, let me also note this. When you are trying to create the equilibrium constant, only utilize values or concentrations of product and reactant when they are at equilibrium. Do not do it at other points. That is known as something different, which I will cover later on in this video and why it's important. But for this purpose, always have the equilibrium constant as just the plugged in versions of the really just the products on top divided by the reactants at the bottom when they're at equilibrium. Okay, now typically on most questions you're going to be told that they're at equilibrium based off some keyword, right? They're literally going to say it's at equilibrium probably. And there's one little caveat to this as well. So suppose that in my reaction right here, instead of having A plus B is C, I had 2A. And with knowledge of kinetics, if you were to apply that, that would have made a squared right here, okay? So you would also have to transfer that square into here as well. So that would also prompt a somewhat different change. So like, yes, I understand that when you have like the concentrations listed out, A will be a certain amount, you have to square that value, and that's applicable to any case. So if I had a 2C, I would have to square it. If I had a 2B, I'd have to square it when I'm writing my equilibrium constant. Whenever you have a coefficient, which is really just the rule of thumb, a coefficient in the reaction and coefficient in the reaction equation, you make it an exponent in the equilibrium constant equation. Is equal to an exponent there. So that's kind of like what it is, but let me go a little bit more in depth because a lot of people don't understand why things like being in equilibrium, and it's really this idea of actually Gibbs free energy. And if I were to write delta, no, not delta G, but just regular G here, G. So and Gibbs free energy is the total amount of available work in a system. And I were to basically write here the number of concentration. Okay. And assume and of reactant, by the way. Of reactant. Well, actually, hold on. Just put it like this, okay? I don't think there's a y-axis or an x-axis in this case, but just think of delta G, okay? I'm going to draw this little curve right here. This right here is at 0, okay? This is when delta G, the transfer of work and energy between a system or within a reaction, is 0. And why is that? And why does it occur here? Because here is the lowest point of energy, okay? And this sounds confusing at first, but hear me out. When the reaction is here, there's going to be more reactant than product, okay? Than product. If the reaction is here, there's going to be more product than reactant, okay? So the way that we can understand equilibriums is a system is trying to achieve the lowest state of energy. So when the products are greater in energy, by the way, right, when I'm creating this inequality sign, it's straight up talking about energy. And this is typically when there's a lot of product and very little amounts of reactant. If I have a lot of energy in my products and very low amounts of my reactant, I'm going to start trying to shove myself all the way down. That's why delta G is equal to negative. That means that the overall reaction is losing energy. And this is a little bit of thermodynamics, but it's vital to understand equilibriums through this lens because everything is based off thermodynamics. So if we recognize that delta G is negative when products are greater than reactants, and also true when delta G is negative when the reactant is so much more in energy than product. And I want you to think about why that makes sense, because assume that there's so much reactant. If you have a lot of molecules can do a lot of work. And if you have very little product, it obviously the system wants to favor a state in which it can minimize the amount of available work by going through a reaction, right? Because as reactions continue, there is either energy released or energy gained. So if the reaction can go through, meaning that delta G would have to be negative because negative delta G means spontaneity of a reaction, right? Then it can essentially reach a point in which it's 0, right? Because the reaction isn't going to keep on, like, put it like this, a reaction will continue to go and continue to be going forward as long as it's going to lose overall energy, right? So the only time it's going to stop is when it's at 0. It's not going to go positive, by the way. So once this equilibrium is reached right here at 0, it's not going to go upwards, right? It doesn't want to go positive in energy. It wants to stay at that lowest point, and that is why it's going to stay at that lowest point. Once an equilibrium is reached, unless an outside force basically damages it or penetrates through the system, this is what is always going to be like at that state. Like, most things are going to end up wanting to be at equilibrium because it's so favorable, because either and I say this because originally the reactant had to have way more energy than the product, prompting the reactant to go forward and become product, or the product had so much, right, and it's trying to go forward and become a reactant, all right, and that's like the reverse reaction until the point that it becomes zero in the change of energy, because at that point it's like, okay, well, I don't really want to lose energy becoming, or by going through this reaction, I'm not going to lose any more energy or available work, because at this point it's just useless, so they're going to stay at a constant rate. Does this mean, by the way, does this mean that when equilibrium is reached, um, does a reaction end? A lot of people wonder. And when E is, by the way, for equilibrium is reached, does a reaction end? The answer is no. The answer is no. It doesn't mean the reaction is going to end. It just means that the reaction will essentially be at, let's say 5 molecules are going forward. 5 molecules will then be going backwards and getting decomposed, and 5 will be composed, okay? That's what I mean. There is no end of reaction when an equilibrium is hit, okay? Additionally, I want to make one more final point when it comes to equilibriums, especially with what they are and why they're important. Note that you always should relate it to delta G. Okay, delta G is 0 at equilibrium, and this is going to come in handy when thermodynamics are used typically, because equilibriums go hand in hand. But note that the reason that all of this is happening is because you want to have delta G at 0, and when delta G is 0, that basically means the change in energy as the reaction is going is literally nothing. And as a result of that, that should kind of signal that it's a little bit of an equilibrium, because as the reaction goes forward, there's no energy being lost, no available energy being lost, but as the reaction goes backward, it means no energy is also being lost either. So that's a perfect state. It's the lowest state it could be at. Okay, so equilibrium is the lowest state of reaction, and typically when these equilibriums are being reached, concentrations are going to remain equal. All right, so that's that. I want to quickly go over notation as well, because there's so many ways that you can see equilibriums, and it gets really, really confusing for people. So you're going to have typically a normal equilibrium being in Kc, okay, and I'm going to go over like conventions now before I go into any more content, because conventions are important to know. So you have Kc, and these are for normal equilibriums. You're going to have Ksp. These are for equilibriums relating to salts in water, so aqueous solutions. You're going to see a lot of Kp. This is equilibriums relating to gas. Okay, there is an equation to relate Kp and Kc. However, you don't need to know that for the AP test, but it does depend on what class you are in, because your classroom teacher may want you to know that. So honestly, that would be something I would Google personally. I'm just trying to cover AP content in this video, but you do not need to know how to convert Kc to Kp. The real difference between Kc and Kp is that Kp is an ATM when measuring it, and Kc is always going to be in a molar, or like you're utilizing molarity, right? You're utilizing molarity of a substance or of its reactants and products to determine what the constant is, whereas in Kp you're just using ATM. There's also going to be things relating specifically to acids. You're going to have Kw. This is the autoionization constant of water. That's going to be elaborated more on when it comes to acid and bases. You're going to have Ka, which is the equilibrium constant of acids, of typically weak acids, by the way, and you're going to have Kb, which is the equilibrium constant of weak bases. All right, and note that it's only for weak acids and weak bases. They typically don't use Ka and Kb for very strong acids and strong bases. Again, not content that I'm going to cover because it's not necessarily related to this completely, but it's still useful to kind of keep in mind. Anyways, so that being said, let me explain another important key concept that kind of relates to what I was previously talking about, and this is the idea of the reaction quotient. The reaction quotient isn't necessarily a hard concept to understand, but its application is actually pretty useful. So the reaction quotient basically is the following. Assume that you have a reaction that is just starting and has not hit equilibrium, okay? If I were to get all the concentrations at that given moment, all right, at the given moment before equilibrium, anytime before equilibrium is reached, like let's say equilibrium is reached after 30 seconds of a reaction happening, well, if I were to get it at 10 seconds, 15 seconds, or 20 seconds, it doesn't matter, just the concentrations of the reactions, products and reactants at a time before the equilibrium, when you put them in the formula for the equilibrium constant, so, remember, this is products over reactants. You got products over reactants, and you have the power that they're going to be raised to based off their coefficients, right? If I were to get a time before the equilibrium is reached, and I were to put in my concentrations for my products and my reactants, that is what my reaction quotient is. So assume that my equilibrium, I'm going to denote it as E here, is 30 seconds. That's when it's reached, okay? If I were to go at 15 seconds and figure out, okay, well, how much product do I have? How much reactant do I have? All right, and I were to put it in this equation, I would get a different value than K, because remember, K is only the values of the equilibrium concentrations, not what is happening before. What we denote the reaction quotient is the value of Q. Okay, so Q is the reaction quotient, and K is equilibrium quotient. The only difference is the type of the concentrations we are using in reaction quotient are not when equilibrium is reached. Okay, that's literally it. And the reason that this is so helpful is that we can now dictate which direction a reaction is most likely going to go forwards or towards when we have the K value and then we have the current Q value. What does that mean? So suppose my K value is equal to 4, okay? But my Q value right now, and let's say my equilibrium is reached again at 30 seconds, but at 25 seconds, I have a Q value of 2. Okay, well, that means that as in the next 5 seconds, my reaction is going to go and create concentrations such that my Q value is going to become K and 2 is going to become 4. So then you ask yourself, okay, how do I get a value of 2 to become 4? You have to obviously increase the value of that, right? So typically when a reaction is going, right, what do you have to do, right? Do I increase the products? And I simply just want you to, in this case, always write products over reactants, okay? Well, in normal mathematics, if you want to increase the size of a fraction, you typically increase the amount of product that you have. For example, if I have 2 over 1 and I want to make it this larger, I'm going to go like, okay, 5 over, and obviously this is going to get a little bit smaller as reactants are consumed during the reaction, but like 0.9. Right? This is still going to be larger, and if you just simply go to a calculator, 5 divided by 0.9, right, it's 5.555 as opposed to 2 over 1, which is merely 2, right? So products are probably going to have to get bigger. Granted, reactants will get smaller a little bit as well, but because the products are going to have to get bigger to reach that value, we're going to say that the reaction, if, right, K is greater than Q, is going to be product sided. If Q is less than K, it's literally the same gist. Whereas, like, for example, well, not the reaction necessarily isn't product sided, but it's going to go towards the products. That's a better vocabulary to be used. Towards products. Okay, it's towards products. If Q is less than K, it's going to go towards reactants. And the reason for that is you simply have to increase the amount of reactants and reduce the amount of products, right? And towards reactants. And obviously, if Q is equal to K, you're already at equilibrium, so it's not going to go towards any direction. There's another thing that I want to note, and this is just basically identifying and classifying reactions using the value of K. If K is greater than 1, we basically say that it's going to be a product. That's why I was using the word product cited incorrectly. I want to use it in this case. If K is greater than 1, right, and they note it like 2 equal signs, or not equal, but greater than equal signs, we're going to say it's product cited. Why? Because it probably means that there's a lot of product and very little amounts of reactant, right? Because I mean, and that's in relative term, by the way. Like, you can have like a lot of reactant, but you just have to have way more product in general. That's when equilibrium is reached. That's when the system finds it most favorable to basically stop favoring one side or the other. It's just going to be product sided. If K is less than 1, and this is typically going to be the case when you're having like salts, K is typically less than 1, it's going to be reactant sided. And the reason for that, if you just look at it mathematically, is like you're going to have a K less than 1 if you have like 10 over like 1,000, right? But if you have K greater than 1, and obviously this demonstrates then that there is more product than reactant overall. And by the way, when I say product, I mean holistically, because there could be like 3 or 4 products, but we're talking about product in general. So when I say product, again, remember, it's not just one, like if I have A plus B is equal to C plus D, so A plus B, C plus D. When I say product, I don't only mean C, I mean both of these combined. Okay, that's the entire product, right? Whereas if I have K is greater than 1, I have to have like 100 over 2, right? To have a pot or a non-fractional value. So that obviously means that there's going to be more product overall in the reaction, and that is going to be the way that the reaction is going to be orienting itself, that there's going to be more product than reactant naturally, and that's why I say that. And that kind of relates to this case, right? Where if I want to go from like, let's say Q of 2 to 4, right? That obviously demonstrates that I have to increase my products to essentially reach there, at the expense of reducing my reactants, right? Which further demonstrates that it's going to be somewhat product sided inherently. So that's kind of like the notation stuff. There's one more thing I want to talk about notation, and it's really this idea that you do not include liquids or solids in your equilibrium expressions. So what an equilibrium expression basically is just the value of like product over reactant. That's literally what an equilibrium expression is. It's nothing too serious. Okay, so that's that. And let me give you an example, and I'm going to give 2. Suppose that I have H2O plus an acid, HF. Don't really have to know what it becomes yet if you haven't reached this part of the later chapters about acids. By the way, this is the notation for equilibriums. It's just a line with 2 arrows, or it could be like this. These are the 2 ways you write equilibriums. But suppose I have H2O plus hydrofluoric acid in equilibrium with a proton, right, and F minus. Okay, these are all aqueous. This is a liquid. If I'm going to write my product over my reactants, which is going to be K, by the way, this is going to be a Ka situation. HF is a weak acid. I'm going to write it like this. H plus, right, product, multiplied by my product, over HF. I'm not going to include water because water is liquid. And typically, by the way, on equations like this, they're going to denote the state of matter that the values are going to be at. Additionally, if I were to have something different where it was a solid, right? So let's just assume that this water is actually ice. I would still not include it, okay? Another example would be like if I were to have NaCl, right, which is a salt, and I were to dispense it or put it in water, and I were to get Na plus and Cl. This is an example, by the way, where I would use KSB because it's a salt in aqueous solution, okay? I would say, oh, it's merely just Na plus and Cl concentrations and molar. I would not include the salt, okay? So these are examples in which, and it's really just if there's a solid or if there's a liquid, do not include it as part of the reactant or product. Okay, I know that these ones were product based, or I mean reactant sided liquids and gases, but if I were to create a gas here, yeah, you still wouldn't include it. Or if I were, not a gas, sorry, solid and liquid. If I were to include a liquid here, I still would not include it on the top region. I would not include it in the product region. Okay, so that's really like the primary way of understanding equilibriums and notations. Now I kind of want to just introduce a little bit of the, like, it's weird to say, but like the mathematics of this, and I want to kind of cover this quickly because these are stuff that you kind of have to do practice with. But really, by the way, this is going to be on the AP test if you take it in future years, but suppose that I have Kc, right, of one reaction. And I say my Kc is 5, right? And it's of A plus B is equal to C. All right? So if that's the case, my K value is going to be the following, right? It's going to be C over A plus B. All right? That's the Kc of this. Suppose I were, though, to flip my reaction in which I say, okay, C is going to decompose into A plus B. Well, are you going to have the same equilibrium constant value? The answer is no, because now what my reactants were originally are now my products, and what my reactant is now was originally my product. That sounded really trippy. Let me go over this. What my products were once, or I'm sorry, what my reactants were originally are now my products, and what my product is now, or what my product was, is now my reactant. So how would I represent this? I would say, oh, it's just simply K of, and by the way, I don't know why I did A plus B. It's two separate things. I would do it like this now with this new reaction right here. So this is my first reaction, and that's what I have here. This is my second reaction where I have, oh, okay, the A and B are going to be on the top here, and the C is going to be on the bottom. Boom. So my question to you is, how are we going to then, like, without having to do this like rejiggering of work to really understand it, what is a quick mathematical solution for this? Well, if this is what this is, but only flipped, these are called reciprocals, okay? So the best way to find if you're flipping a reaction, the new equilibrium constant is simply doing 1 over Kc. You're just flipping it. That's simply all you're doing. That is the equilibrium constant for the, not reverse reaction, but the flipped reaction, okay? Another case. Suppose I were to say, okay, A plus B is equal to C, or goes to C. What happens if I say, well, you know what? I want to double everything I do. So double this, and double that. All right? Well, my new equilibrium constant, using this old one right here, is going to be the following. It's going to be C squared, A squared, B squared. Whenever I multiply the same coefficient, or the same like integer, to the entire reaction, I am allowed to basically say the following: K to the power of that exponent, or to that, exponent, which is equivalent to the coefficient, because everything just got squared here. So the other way of writing this is just C A times B, and I'll just put the brackets, boom, 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 and I could just say squared. These are all mathematical conventions, by the way, so it's important to know at least algebra 2 when I'm talking about all this stuff. So boom, you have that, and I would say, like in this case, I would have said just, oh, K is squared. That's it. All right. If I had 3A plus 3B going to 3C, it would just be K cubed. All right, so on and so forth. And lastly is adding reactions that are both in equilibrium. Okay, so suppose I have the following. I have A plus B going to C, and C plus D going to, C plus D going to E. Okay, so I'm going to quickly show you everything here. So if this is the case, right, A plus B is going to C, and let me write the reaction form, by the way. I always forget to write reaction formulas, or like not formulas, but signs, but you have to note that these are all in equilibrium by doing the two arrow signs, all right? This is E, okay? So what is the reaction constant for this, okay? Well, it's going to be C over A times B, and I'm not going to really bother writing brackets, but kind of note that this means this, this means this, this means this, right? And for this one, it's going to be what? It's going to be no longer C on the top, but E on the top, and C times D, okay? So what happens if I were to add these reactions, all right? So I would say, okay, you got A plus B plus C plus D, and it's going to be an equilibrium with C and E. Okay, well, this and this are going to cancel out, right, because they're on both sides of the reaction. So I'm going to have A. Oh my god, I have trouble writing B's and D's. But anyways, you're going to have A plus D plus B is a reaction, or an equilibrium with E, because C is going to get consumed both ways. And now my new equilibrium constant is going to be just E over A times D times B. Okay, so why is, like, look at, I just did all this work, which is going to be very, very long, but I'm going to make it simple for you because this is a new trick that you should know. What you would do if you have to add two reactions that are in equilibrium is the following. You multiply the reaction constants. So if this is K1 for reaction 1 right here, and this is K2, all I would do to get K3, which is this value right here, K3, is do K1 times K2, and let me show you the proof for that. Simply do C of AB times E over CD. The C's cancel out, and now you have A times B times D, which is E over A, B, D. Boom, that's the same, and you multiplied these. So these are all conventions that you should know, and sometimes, to be a little bit tricky with you, the AP College Board is going to incorporate all components together. They're going to try to add stuff a lot at you, okay? By the way, this is just merely an application of Hess's law in thermodynamics. Okay? Application, oh, that was really messy, of Hess. So, without further ado, let's get towards the end of this chapter, and really it's talking about the idea of ice tables, and lastly, Le Chatelier's principle. Okay, so what is an ice table? Because you're going to use this a lot, and this is really going to be your best friend when you're dealing with equilibriums. Ice basically stands for the following. Ice stands for initial change in equilibrium, and I'm just going to denote that as, actually I'll just write it out. So basically, most AP Chem problems and most first-year chemistry problems are going to give you the following. They're going to give you the initial concentration of at least one of the components or the reactants or products. Okay? And I want to note, by the way, that an equilibrium can be reached when you have, and before I cover ice tables, because people are going to get confused, equilibriums can only be reached in the following. If you have all components of one side, okay? That's really the prerequisite. To have an equilibrium means to have a reaction to begin. It's just the most fundamental thing, but sometimes people get confused about this. You're going to need at least one side of all molecules in a reaction. What do I mean by that before I cover ice tables of reaction? What do I mean by that? So if I have A plus B going to equilibrium with C plus D, if I were to originally just put a little bit of C in the system and not have any B and A, that's not going to reach any sort of equilibrium, because C can only react with D to form A and B, so I'm just going to have a dead end reaction right there, or I may have a different reaction. Now, if I were to have C and D, that's cool, because what could end up happening is C and D, right, if I have both of these now, can end up decomposing into A and B, or transforming into A and B, and when I have some A and B can eventually go and become C and D, and they can somehow hash out an equilibrium. But if I were to only have just C, I'm not going to get anywhere. Suppose another scenario where I only have C and I have A as well. Well, A and C are not going to react, okay? Unless they do, they'll form a different reaction. But just because you have one component of both ends does not mean you're going to go into equilibrium, okay? What it does mean is that they can hit each other and form a new reaction that's totally different, but it's not going to be the one you want. You need to have at least one side of all components of a reaction. So you need to have A and B for the reaction to happen. You need C and D for the reaction to happen. It doesn't mean that if you don't need A and B, by the way, if you have C and D for the reaction to start. It'll be helpful, and it'll actually help the reaction go forwards a little bit quicker because you have some concentrations of both, but it is not necessary or prudent, or yeah, that's the word, I guess, to have both sides completely met. You can do it with just C and D or just A and B. If you have both sides of all molecules there as well, it's still going to obviously go through. It's just that you only need one side completely fully done, okay? And you do not, and by the way, A and C or B and D, right? If you only have A and C or B and C or B and D, nothing is going to happen, because those two are not going to react together to form the reaction you want, okay? Anyways, let's go to ice tables. Typically, what most AP Chem and first-year chemistry classes are going to give you is one, and they like being easy on you. They're just going to give you a lot of just A, for example. They're going to be like, yeah, you have A and B, right? Here are your concentrations for both of these. You have 0 of this and this. So what they're essentially going to tell you is, oh, okay, you have, like, let's say 4 molar of A, and let's just do a new reaction here, and I'm going to just show you. You have A and then B and C, right? You have 4 molar of A and 0 of this and this. So these are my initial concentrations, right? It's saying initially you're going to have 4 molar of of reactant A, and you're going to have 0 of B and C because B and C haven't been met yet. So A is essentially going to have to decompose, right? So what is my change, right? My change is going to be essentially I'm going to lose a certain amount, right, to become because it's going to decompose, and the amount I lose is going to be the amount I gain in this, right? So X and X, right? X plus X right here. Suppose that, and I'm going to write A here and B here to note this. Suppose that I had, instead of, for every 1A that is lost, I get 2B, I would have to write 2X here. Why? Simply think about it. If I were to lose 1 molecule of A, 2 molecules of B would be formed. So my change, by the way, the reason I say minus X here, by the way, is because you're losing. But my change, if this was a 2, would be having 2X right here. All right? I hope that makes sense, because if I'm losing 1 molar, or like a molar amount of A, right, that's minus X, I'm going to get double the amount of that. And suppose that was a 3, I'd get triple, so I'd write that as a 3. All right, but back to making it pretty easy again, I would just simply say, okay, I have X and X. All right, so that's my change. And what is my equilibrium going to be then, right? I'm going to have, well, then 4 minus X, and I'm going to have 0 plus X and 0 plus X. These two, by the way, can be different values if there was some concentration of the products remaining. So if there was some B and C, they would not just be 0. It would be like 3 plus X if B was at 3. Okay. So, but right now in this case, it's going to be 0 and 0. So now that I have these algebraic formulas, what I'm going to do is the following. I'm going to put them in the equilibrium constant equation, right? And that's just the product over reactant, and that's simply going to be the following. Well, my products are B and C, so I've denoted this as 0 plus X and 0 plus X, so I'm just going to say X times X, and then my reactant is just 4 minus X. Okay, so that's going to be X squared divided by 4 minus X. Okay, this right here is my equilibrium expression. You can figure out, by the way, the purpose of ice tables is to figure out concentrations at equilibrium sometimes. So if I knew what X was, I would just be able to plug these in and get my K value. But typically what you're going to have to do is they're going to give you what the historic K value is. Like, most scientists already know most K values for a lot of reactions. So they're going to give you the K value, and they're going to say, okay, tell me what the concentrations are for most of these things. So I'm going to say, okay, X squared minus 4 divided by 4 minus X. If it's like 4 is equal to K, so I just do that. I solve it algebraically for what X is. And then I'm going to plug it back into these expressions right here at the very end, because this is telling me what my concentrations are at equilibrium. That's why it's E, the equilibrium concentrations. I'm going to plug in what X is at the very end of my algebraic expression when I know what K is. Right? I'm going to plug it in back here. And then essentially what I'm going to get is the equilibrium concentrations for all the values. That is how you use an ice table, and that is really most of the math you're going to have for most of the equilibrium unit. All right. And lastly, and this is the final concept, so yay, you're going to have the Le Chatelier's principle. This is huge. All right. And there's really 5 components of Le Chatelier's principle, essentially 4, but I like to say 5. We'll keep it at 5. This is basically a way of explaining things to this is relating phenomena to equilibriums. That's what Le Chatelier's principle is. Le Chatelier's principle's primary goal is basically to assert the following. Assume you have a stable equilibrium. What will happen if I were to throw that equilibrium off? What would happen if I were to add another variable? Remember how I said that equilibriums will always remain at equilibrium unless there is an extra force added to it? This is the case. It's like if a car is going on a straight road, the only reason the car is going to turn, unless, you have to reach your destination, like assume there's a really, really long road, right, and you're going to drive on that road forever, the only reason that you would have to pivot or change your direction is if there's a dead end, or if there is like an alternative route, or if like another car comes in front of you, or if you get into an accident. Assume that there is something that gets added, another variable, and it disturbs the equilibrium. It shoots it off course, okay? And I'm going to now explain to you what will shoot equilibriums off course and how And this is what Le Chatelier's principle is going to do. It's going to explain to you how equilibriums are going to be reestablished. Okay? Number one, concentrations are going to be the biggest thing that's going to impact equilibriums. Concentrations. So what does that mean, right? This means that if I have A plus B is going to be in equilibrium with C, and I add a bunch of A, right? That essentially turns this into the following. I'm going to have a higher amount of reactant, right? And I want you to compare this, by the way, to delta G. All right, I want you to compare this to delta G because it's going to be very, very helpful to understand this. If I were to add a lot of reactant, all right, so what does that mean? Like if I were to add a lot of A into my system, okay, so that means that the energy in A plus B is going to be increased, right? And that means that it's no longer going to be the same amount of energy present within the system that C has. So remember that thing I had. I'm going to try to pull it up here. Remember when I had reactant and product? Now my reactant is going to be greater. Like if originally I was here and I was at equilibrium, I'm back to here. So what's going to end up happening is that my delta G is going to become negative, and I'm going to push forward C. So this can also be applicable to the opposing reaction. So if I were to have very little amounts of C, and I wanted to get, well, hold on, let me actually make this clear, by the way. By adding a lot of A, right, I'm going to make delta G negative, which means that I'm going to go towards C, okay? So by adding more reactants, essentially at increasing concentration of reactants, I'm going to increase, or I'm going to push forward to my product, okay? I'm going to push forward product because delta G is going to be negative, and obviously you can also relate this to Q and K. If you want to as well, right? So these are all kind of interconnected. By the way, if I increase concentration, I'm also increasing the rate of reaction, so I'm going to kind of go towards C a little bit inherently. Anyways, that being said, I could do the same thing, but utilizing an increased concentration of C. If I increase, and this is when we're at equilibrium, by the way. If we're at equilibrium and I increase my concentration of C, right? If I were to go back to this, if I was originally here and now I have more product because I've increased my concentration of C, I'm going to push downwards, meaning that my delta G is going to be negative with respect to going this way. All right? So that means I'm going to create more reactant in the reaction. Okay? Now, this can also be done by removing some amount of concentration. Okay? Suppose I have an equilibrium and I say, okay, I'm going to take out half of the C molecules that I have. Inherently, I've reduced the amount of available energy within the amount of C. So I'm going to have to push forward more A and B because A and B now have more energy in general than C does. And that is what's going to prompt something like that to occur. This can also be so with A plus B. If I reduce the concentrations of A plus B, that inherently means that I've increased, or inherently means that I have higher C concentrations than I originally did. That means I'm going to have to push towards A and B if that's the case. This is all delta G related, okay? And this is very, very much used in chemical industries because suppose if I'm at equilibrium, my concentrations aren't changing, but I really, really want to push a lot of my product out. If I want to push a lot of my product out, I'd say, okay, you know what? This is what I'm going to do. I'm going to add more and more reactant, or I'm going to take out the product I currently have in my system so I can flush out most of my A and B by essentially reducing the energy of my C so that the energy of A and B are going to be higher, okay? But when I say removing concentrations, suppose that we're at equilibrium, and I want to do this on the diagram again. Suppose we're at equilibrium and I reduce my C. That means that A and B inherently now have more energy than C because when you have less molecules of C, you're going to have less energy in general. It's going to then push forward this way, okay? That's one thing, concentrations. Next thing is pressure. If I were to do pressure, I also have to relate this to volume. These are mostly volume-related problems when you have anything that says, oh, the pressure changes. So always think of volume. So obviously when I increase my volume, my pressure decreases. And when I were to decrease my volume, my pressure will increase because there's going to be more collisions, right? So if I were to increase volume, right? So increase volume, V, and this is, by the way, just stuff with the gas law. So increasing V means that I decrease P, right? If that's the case, what's going to end up happening is the following. Concentrations are going to change simply because if you think of PV is equal to nRT. All right, so P is equal to nRT over V. And I were to kind of isolate variables and say N over V times RT. By changing my V value, and by the way, N over V is exactly what molar means, by the way. This is the equation for molarity. So if I were to increase my V, I've inherently reduced everything. Okay, inherently I have reduced everything. So, and that means I have reduced my concentrations, and this is simply like an application of concentration change, except in this case it was adding molecules, so this was much more direct. This is an indirect way of changing concentration by changing my volume. So as a result of that, and you can also relate this to delta G, but it's going to get really, really convoluted, and I don't want to do it. But if my volume increases and my pressure decreases, and I have A plus B is in equilibrium with C, what's going to end up happening is I'm going to try to reverse this effect by increasing my pressure. And I'm going to increase, or I'm going to be able to increase my pressure if I increase the amount of moles that I have. Remember, if you have more moles, that means more collisions. So what I'm going to end up, or more molecules, what I'm going to end up doing is if I have a reaction like this, C is going to become more towards A. Okay? Simply the reason for that is that if I reduce my pressure, I want to regain more pressure, so I'm going to start favoring A plus B. Okay? Alright. There's also a way you can do this with like total pressures. So if I inherently like concentration can be basically described as like the partial pressure, so PP over total pressure. And if I change the partial pressure of everything, I'm inherently changing its concentration. All right. So, but anyways, so if we reduce pressure by increasing volume, we're going to favor the reaction that increases the amount of moles. If I were to, however, switch this up and say, oh, we reduced volume, meaning that we increased pressure, we are going to favor the side that will reduce the amount of moles because we want to reduce the pressure. We want to reduce collisions. So in this case, A plus B is going to go towards C because there's less moles. Okay, that's the effect of pressure and volume. Next up is going to be the impact of temperature. And by the way, I want to note that in these cases, by the way, the K constant is still going to be the same. In this case, in temperature, when you increase or decrease temperature, you're actually going to change your K value. And now I'm going to also explain what direction your K value is going to go towards, by the way. But you're going to change your K value, and you're going to ask, okay, well, how does that make sense? Let me show you, right? If we were to go back all the way towards here, and I demonstrated to you that this KR and KF thing are equivalent to this right here, the expression for equilibriums. And if I change my temperature, right? If I change my temperature, what am I going to be also doing? I'm going to be changing my KF and my KR, because my KF and my KR are what I call my my rate constants, and my rate constants can be expressed as this: K, or a rate constant K, right? This is not the same thing as my equilibrium constant, but my rate constant K is AE minus activation energy over RT. All right, so by inherently changing my temperature, I'm going to be inherently changing my K values. All right, that's why changing temperature, that's the direct link to how the K values are going to change. All right, and this is the only case in which your K value is going to change. But let me explain how you can determine what direction your equilibrium is going to lay once your K value changes by changing temperature. This is completely dependent on endothermic and exothermic reactions. If you have an endothermic reaction, the best way to think about it is the following: that you are essentially keeping in heat. Heat is going to be like a reactant. It is going to be something that you take in, right? So I'm going to assume heat is going to be a reactant. You're going to kind of be confused by this, but just assume it. Okay? So A plus heat is going to form B. Okay? And if I were to increase my temperature, right, what does that inherently mean? And assume this is at equilibrium, right? What does that inherently mean if I increase temperature, right? I'm going to be creating more and more heat, okay? Right? Because as I increase temperature, my rate of reaction increases. That means that more molecules are typically going to be able to kind of like pass through the reaction and like reach equilibrium. And as a result of that, right? I'm going to form more heat, and by forming more heat, I formed more reactant, and if you treat this as a reactant, I'm going to have to go towards B. Okay? Consider the following if I have exothermic. Exothermic, my heat is going to be part of my products, right? Assume this, right? If you're exothermic, you're releasing heat. That's kind of like a product in a way, right? So A is going to form B plus heat. Well, if I were to increase my temperature, that means I'm going to increase the amount of molecules, or really the amount of stuff that is going to be made, right? Because I'm reaching closer to the activation energy. I'm also assuming you understand kinetics when I'm explaining this video, but you increase heat, right? So what ends up happening is the following. By increasing temperature, you're going to increase the amount of molecules going and being made into reactant. That means you're increasing the amount of heat because more heat is like the reaction can fully go through. And as a result of that, because more product is being made, it's kind of like the idea of concentrations. You're going to favor towards the left. You're going to favor something that goes towards the left. Okay? And that's really it for temperature, but you should note that the K value does change. Okay? By the way, I'm explaining what happens when temperature increases. Think of this, temperature increases. If temperature decreases, just simply do the reverse of what I just said, right? So play back the video. So in this case, if it's exothermic, and I know that when temperature increases, more A is going to be created, right? Well, when temperature decreases, more B is going to be created. It's just the inverse of everything, okay? That's simply it. Lastly, the role of catalysts. Catalysts do not do anything to the equilibrium. They just make you reach equilibrium quicker because, remember, all you're doing with a catalyst is increasing the speed of the reaction. Okay? That just means that by increasing the speed of the reaction, I'm getting to my equilibrium faster. It's not going to change my equilibrium constant at all, right? And that's really it. And the reason for that, if you look at an energy diagram, right, is like this. Assume that this is my first reaction. This is going to be exothermic. If I were to simply reduce everything, right, all that means is that my products can become my, and this is really the activation energy right here, as opposed to the original larger one. My products are going to become my reactants quicker because the activation energy is lower for it as well, and my reactants are going to become my products quicker as well. It's kind of like a mutualistic thing. That's literally it with catalysts. So it does not impact equilibrium. And lastly, this is the fifth one, dilutions, or increasing concentrations as well. This is really just working with water and aqueous solutions. So this is going to be relating to KSP. KSP related. If I were to increase or add water, if I were to add water in a KSP reaction, right, or in an aqueous reaction, I'm going to favor reactants. And you're going to be asking me, oh, well, why, Parsa? Well, the reason for that is the following. Water is inherently part of a reactant, or no, it's not going to favor reactants. Oh my god, I'm so sorry. Ignore that. It's going to favor products. Sorry, I lost my mind there. All right, it's going to favor products, okay? If you add water, it's going to favor products. And this is only in KSP reactions, so when you have a salt becoming its aqueous portions. Why? Because water is a reactant, right? So if I have NaCl, NaCl is reacting with H2O, right, to go into equilibrium with Na plus and Cl. The only reason that I never wrote, H2O in the reaction quotient is because of that rule that scientists have that you don't add anything that's a liquid, right, or a solid, by the way, again, into the reaction equilibrium expression, right? But inherently, if I'm adding more water, I'm like adding more concentration. It's going to favor this. That's really it. Dilutions are going to favor the products, okay? Dilutions favor products. Concentrations, meaning I remove water, are going to favor the solid state, basically. All right? And the NaCl here would be a solid, too. Okay? That's really it with most of Unit 7. I know it was a lot, but I hope it was a comprehensive review that explained a lot of the whys. So, yeah. Hope that helped. See ya.